This lesson shows you how to execute code repeatedly using loops. A while loop executes code until a condition is met. When a while loop executes, it first executes the code inside the loop. Then it checks whether the condition has been met. If the condition has not been met, the while loop repeats the code until the condition has been met. When the condition is met, the while loop exits. If you're familiar with text-based programming, a while loop is similar to a do-while loop or repeat until loop. The iteration terminal outputs the current loop iteration count. The first iteration is 0. The conditional terminal can be configured in one of two ways: either to stop the loop if the Boolean value is true, or to continue to repeat code if the Boolean value is true. Tunnels transfer data into and out of a loop. This while loop has two tunnels, one input tunnel and one output tunnel. The while loop does not begin executing until it receives data at all of its input tunnels. In addition, the while loop does not pass any data out of its output tunnels until the while loop has terminated. You can wire an error wire to the conditional terminal to stop the while loop. If you wire an error wire to the conditional terminal or an OR function, only the true or false value of the error status is passed. In the following example, the while loop stops when either the user clicks the stop button or the VI outputs an error. Currently, when I run this VI, the VI runs the code once and then stops. Let's modify this VI to execute the code repeatedly using a while loop. To create a while loop, go to the Functions palette and select While Loop. Then click and drag to place the while loop on the block diagram. Now I'll create an indicator for the loop iteration terminal and a stop button for the conditional terminal. I'll change the loop iteration indicator display format to decimal. Now I'll run the VI again. Notice that the VI is running the code inside the loop repeatedly, as fast as possible. When I click the stop button, the while loop exits, and so does the VI. If I run this VI with highlight execution turned on, you can see that the loop iteration terminal outputs 0 on the first iteration and then continues to increment it. Now let's see how an output tunnel behaves. Notice that the output tunnel does not pass any data until the while loop finishes executing. Now let's see how an input tunnel behaves. Notice that the while loop will not start executing until it receives data on its input tunnel. Notice that when the loop begins executing, the input tunnel will only output the original data it received because input tunnels only read data once. If I change the value of the total time in seconds control after the while loop has started executing, the while loop input tunnel will not read the updated value. A for loop executes code a set number of times. In this example, the for loop executes the code 100 times. The value in the end input terminal specifies how many times to repeat the code in the for loop. The iteration terminal outputs the number of the current loop iteration. The first iteration starts at 0. To create a for loop, open this palette and select For Loop. Then click and drag to place it down. Next, I place a random number generator function inside the for loop and create an indicator. Then, I create a constant for the n input. This input tells the for loop how many times to execute the code inside the loop. I'll set it to 5. Finally, I'll create an indicator for the loop iteration. Now I turn on Highlight Execution and run this VI. As you can see, the for loop runs the code inside the loop 5 times, as indicated by this n input. And because the iteration terminal count started at 0, the final value is 4. If necessary, you can add a conditional terminal to a for loop by right-clicking the for loop and selecting the conditional terminal. Notice a red dot appears in the corner of an end terminal in the following figure when the conditional terminal is enabled. A for loop with a conditional terminal executes until the condition is met or until all iterations are complete, whichever happens first. The number of iterations a for loop executes must be specified in non-negative integers. If you wire floating point numeric type to the end terminal, LabVIEW converts the floating point value to a signed 32-bit integer. When this happens, a red coercion dot appears on the end terminal, as shown in the following figure. A for loop can only execute an integer number of times. For example, a for loop cannot execute 3.75 times. If you need to wire a floating point numeric type to the end terminal, you can make the conversion more explicit on the block diagram by using the toSigned 32-bit integer function as shown in the following figure. Here is a summary of the loop comparison. For loop executes a set number of times unless a conditional terminal is added. Can execute 0 times. Tunnels automatically output an array of data. While loop stops executing only if the value at the conditional terminal meets the condition. Must execute at least once. Tunnels automatically output the last value. Why do you need timing in a VI? You might need to set the frequency of a loop. For example, you might need your loop to execute its code at a rate of once every 2 seconds. 2. You might need to tell your loop to allow the CPU to complete other tasks. 3. You might need to determine how much time has elapsed while the loop is running. The loop in this figure generates a random number once every 100 milliseconds. The vast majority of the time, using the waitMs function is sufficient. When the elapsed time ExpressVI executes, it returns how much time has elapsed since the first time this ExpressVI was called, or since the last time it was reset. This ExpressVI also returns whether the target time, for example, 10 seconds, has elapsed yet. The elapsed time ExpressVI does not do any actual waiting. It only returns elapsed time data when called. If you want to set the frequency of a loop, you can use the wait until next ms multiple function. In this example, we want the loop to execute once every second, so we set this input to 1000 milliseconds. On the first iteration of the loop, the wait until next multiple function waits until the OS clock reaches the next 1000 millisecond multiple, so the first iteration will probably take less than 1000 milliseconds. However, after this first iteration, This function makes all iterations execute once every 1,000 milliseconds by waiting until the OS clock hits multiples of 1,000 milliseconds. If you do not have a wait function in a loop, the loop will repeatedly execute code as fast as possible. This will cause the CPU usage to increase. Here, the CPU usage has gone up to 60%. By using the wait function to add even a small amount of wait to the loop, you can allow the CPU time to complete other tasks and dramatically decrease the CPU usage. As you can see, the CPU usage is now down close to 30. This example executes a straight-line equation calculation, gets the current time, and displays elapsed time information. The loop stops when this output passes a true value. The elapsed time express VI does not do any actual waiting. It just returns elapsed time information immediately. So this loop is executing as fast as possible and has a high CPU usage. To decrease the CPU usage, add a wait function inside the loop. When using the DACMX API to continuously read or write data, you should create, configure, and start the task first. Then you should continuously read or write data in a loop. After the loop exits, clear the task. In this example, the VI creates a task using the DACMX Create Channel VI. The VI configures the task by using the DACMX Timing VI set to the Continuous Samples sample mode, and sets the sample rate and number of samples. Then the VI starts the task using the DACMX Start VI. In the while loop, the DACMX read continuously reads multiple samples until the user clicks the Stop button. After the while loop exits, the DACMX Clear shuts down the task, and the VI checks for errors. Let's talk about how the acquired data gets to your VI. First, the DAC device acquires samples of the signal at the specified sample rate, for example, 10 Hz, and stores these samples in the buffer on the DAC device hardware. Then these samples get automatically transferred to a buffer on the PC. Finally, when your VI calls the DACMX read, this VI pulls the specified number of samples out of the PC buffer. The DACMX read VI waits until the requested amount of data is available from the PC buffer. In this example, the DACMX read waits until 1,000 samples are available to read in the PC buffer. This built-in wait allows the CPU to perform other tasks while the DACMX read is waiting for samples to become available. Let's examine how the desired sample rate and number of samples affect how long the DACMX read VI waits and how often the graph indicator updates. Right now, the sample rate is 1,000 Hz, and the number of samples to read is 1,000 samples. Now I'll run the VI. Notice that the VI continuously acquires and displays data until you click the Stop button. Notice that the data graph updates about once per second. That's why, for each iteration of the while loop, the DACMX read VI waits approximately 1 second for 1,000 samples to be available to read. It outputs the data as soon as the samples are read. Notice that the CPU usage is low because the DACMX read VI waits, which allows the CPU time to execute other tasks. For example, recording this demo. If I keep the sample rate at 1000 Hz and change the number of samples to 500, how often will the graph on the front panel update? At a sample rate of 1000 Hz, the DACMX read must wait 0.5 seconds for 500 samples to become available. So we should see the graph update every 0.5 seconds. Let's run the VI and see what happens. If I keep the sample rate at 1000 Hz and change the number of samples to 2000, how often will the graph on the front panel update? At a sample rate of 1000 Hz, the DACMX read must wait 2 seconds for 2000 samples to become available, so we should see the graph update every 2 seconds. When using an instrument driver API to continuously read or write data from a non-NI instrument, you should initialize, configure, and initiate the instrument first. Then you can continuously read or write data in a loop. After loop exits, close the instrument. Some instrument drivers require you to initiate the instrument, and others do not. Sometimes when you program with loops, you need to access and use data acquired in a previous loop iteration. For example, if you need to get the average of several temperature readings, you would need to use the value from several previous loop iterations. LabVIEW uses shift registers to store and transfer any type of data, such as numeric, Boolean, or string. Shift registers appear as a pair of terminals directly across from each other on the vertical sides of the loop border. When a loop iteration completes, the shift register terminal on the right border transfers data to the shift register terminal on the left border to be used when the loop iterates again. Let's take a look at an example of using shift registers with the for loop. The for loop shown in the first row of the table is configured to run 2 times and add 2 to the value passed from the shift register each time. Because the left shift register is not initialized, it has a value of 0 before the VI runs the first time. During the first iteration, the VI adds 0 and 2. The value of 2 is passed to the shift register and used during the second iteration of the loop, this time adding 2 plus 2. After the VI completes, the value of the output indicator is 4. Because the shift register is not initialized, when you run the VI a second time, the right shift register holds on to the value of the last iteration, 4 in this case, and passes it back to the left shift register. So the second time the VI runs its 2 loop iterations, the value of the output indicator is 8. The default value of an uninitialized shift register for numeric is 0. For a string, the default value is empty, and for a Boolean, the default value is false. If you want the loop to start with the same value each time the VI runs, you can initialize the shift register with a control or a constant to reset the value for the first iteration of the loop. Here, the shift register is initialized to start with a value of 1 when the loop runs the first time. This means that when the VI completes, the value displayed in the output indicator is 5. A loop can contain more than one shift register. If you have multiple operations that use previous values within a loop, you can use multiple shift registers to store the data values from those different operations. Notice that the shift register pairs are directly across from each other on the edges of the loop. The value of a shift register is stored and passed to its pair terminal directly opposite of it. Here, we are keeping the value of the add operation and the multiply operation. The first iteration of the loop stores a value of 2 in each shift register, and then forwards these to be used in the next iteration. A loop can also contain what are called stacked shift registers, which retain values from multiple previous iterations. The most recent iteration value is stored in the top shift register, and as the loop continues to run, the value from the previous iteration is passed down the stack as new values are added. Now I'll show you how to create a shift register. The first thing you need is a loop, a while loop or a for loop. In this case, I'm going to put down a while loop and wire up its stop terminal. Now I'm going to create the shift register. Simply right-click on the border and select Add Shift Register. Now I have my shift register. What I'm going to do next is initialize my shift register with a value. And now I'm just going to go ahead and wire this up. I'm turning on Highlight Execution and running the VI. A 3 gets put in and a 3 comes out. A 5 gets put in and a 5 comes out. The next thing I want to show you is how to create a shift register from an existing tunnel. So to demo that, I'm going to wire this up, create a tunnel, and I'm going to wire this up to my add function. Now, if you have a tunnel that you want to change into a shift register, simply right-click the tunnel and select Change to Shift Register. So I'll change that to a shift register, and it automatically creates the right shift register, which I can wire up. In this real-world example, we use a shift register to keep track of the maximum value acquired from all loop iterations. First, we initialize our shift register to -infinity. On the first iteration of the loop, this VI acquires a temperature, and then we use the max and min function to compare its two outputs and return the larger value. The first acquired temperature will always be greater than -infinity, so the max and min function will output the first acquired temperature and store it in the shift register. We are using the shift register to store the current maximum value. On the second iteration of the loop, this VI acquires another temperature, and we use the max and min function to compare the acquired temperature to the current maximum value stored in the shift register. If the acquired temperature is less than the current maximum, then the current maximum gets stored back into the shift register. If the acquired temperature is greater than the current maximum, then the acquired temperature gets stored into the shift register as a new maximum. Here's another real-world example where we use a shift register to store whether a Boolean value is true in any loop iteration. In this loop, we want the indicator to output true if a threshold has ever been exceeded, either in the current iteration or a previous loop iteration. First, we initialize the shift register to false. Then, in each loop iteration, we check if the threshold has been exceeded. If the threshold has not been exceeded, the OR function continues to output false and stores a false value in the shift register. However, if the threshold has been exceeded, the OR function outputs true and stores a true in the shift register. Once the shift register contains a true, the shift register continues to output true because of the OR logic. In this way, the shift register keeps track of whether a Boolean value was true in any loop iteration. Now I'll show you how to create a stacked shift register to access values for multiple previous iterations. Right-click the shift register and select Add Element to add an element. You can also resize a shift register to add elements to the stacked shift register. Now I'll wire this diagram. Next, I need to initialize all the elements. Then I'll turn on Highlight Execution and run the VI. As you can see, the top shift register outputs the previous iteration's value. The next shift register in the stack outputs the value from the iteration before, and the shift register below that outputs the value from the iteration before. Here's a summary of what you've learned in this lesson.